Hello, welcome back. Here we're going to talk a little bit about the Seidel-Rappaport propagation model. This is part of our path loss modeling unit in antenna engineering. And we started off with the Frisk free space and talked about the logarithmic link budget. And then we said, well, what about realistic scenarios when you have stuff in the way, when you have multipath, reflections, blockages, diffractions, scatterings, things that really complexify the propagation prediction. But unfortunately, that's where we use most of our antennas, in and around stuff. So here's a nice simple model that'll give you another tool, in addition to the path loss exponent model, into understanding how to model these behaviors so that you can predict how much power gets from antenna 1 to antenna 2. So, how do you increase, practically speaking, the prediction accuracy between two antennas with stuff around them? So we learned that the path loss exponent model had a path standard deviation loss error of, on a good day, 8 to 12 dB, sometimes more. Seidel-Rappaport model, or the partition-based model as it's often called, is a simple model that incorporates just a little bit more of site-specific information. So things that you have to know about the environment. You know, the path loss exponent model didn't really require any site-specific information. It was just looking for the type of the environment. Was this an urban area? Is it a rural area, a forest? And that's all you needed to know. And you crystallize the environment down into one little parameter. So let's talk about how this one works. So let's say I have a map of a building. You see, this is actually a home where some real live map measurements were taken. And the numbers you see here are path loss in dB with respect to 1 meter free space, which means you use the Frisk formula to calculate your loss from an antenna, which in this case the transmitter is down here somewhere. Go out to 1 meter free space, and then whatever you see in this number is the excess path loss to that location in dB. So keep in mind that when it says 50, we're really talking 5 orders of magnitude of decrease. And we have some indoor locations and some outdoor locations. This particular transmitter was operating at 5.8 gigahertz. This is one of the first set of measurements ever taken in what's become the very common 5.8 gigahertz wireless networking band, the unlicensed band. There was a motion to allocate this spectrum in the year early 1995, and that's where these measurements come from. So I have a transmitter, and it's on a utility pole top, about 5 meters high. We're seeing how much power can we get into a home. Maybe you want to distribute wireless internet from the curbside or from your neighborhood base station. So let's take a look at what this is. Well, we could do a path loss exponent here and get one parameter that kind of captures everything. But if we want something that's a little bit more accurate, something that's about 6 dB of standard deviation error, instead we use this partition-based model, which was popularized and formulated in a paper by researchers named Seidel and Rappaport out of Virginia Tech. And their model says path loss is going to be equal to, instead of 10n log base 10, this transmitter separation distance, transmitter receiver separation distance, we're just going to say it's free space loss, and that any additional loss you see is correlated to the number and the type, and by type we mean dB loss per a certain type, the number of a certain type and the loss per that type of each partition that's in the way. Now this is nice because computers are very good at calculating intersections of things. They're very good at taking a blueprint and figuring out what's in the way. So for example, if the transmitter is down here and I've measured, let's pick this office, this front door office here, front office, 41 dB of signal strength. Computers are very good at drawing lines that are straight to a location and intersecting them. You see, we barely missed this tree, so we don't have to have a tree. And say, in this location it is 0 trees. We go through one exterior wall. In this case, it was a brick home, so let's say one brick wall. And we don't go through any of the interior walls. 0 interior walls. And so this loss here is due to free space, according to the model, and then some value that's in excess of that. So the path loss would be 1 times whatever the brick wall loss is. Brick walls are usually anywhere from 12 to 16 dB of loss. So maybe we put a 16 dB here. And then zeros for any other subsequent partitions for this particular location combo. So the nice thing about that is you can organize things very systematically and have a computer do all of your intersection tests on a simple computerized database. Now, of course, there's a trade-off here. You actually have to be able to construct this database, which is no small task in a lot of instances. However, this is supposed to be a down and dirty measurement. You're not going to do a full wave analysis. You don't need to get in there and specify the electrical properties of brick for this model or the type of trees and do a scattering analysis on the individual pieces of foliage on the tree. These are supposed to be rules of thumb. So if you were to go back here and say, oh, 48, how would I intersect that? Well, it looks like it goes through a tree, a wall, an interior wall, and another exterior wall. So in this instance, we would have 1, 2, 1. And in general, those points are lossier. Remember, this is still going to have a lot of variability, but it gives you a tool to getting into a complicated region and quickly getting a nice estimate of path loss. So the basic workings is pretty straightforward. Let's take a look at what you can do. So remember, in the path loss exponent model, we said there were 2 types of problems you could work. There's the modeling problem, where I have site info for the path loss exponent model. Was just the distance between transmitter and receiver and the environment type. Here we've got a blueprint to work with, a little bit more information. So to solve the modeling problem, we put that information in and we get a prediction out. A prediction in dB loss or received signal strength. Now that's the modeling problem. The other problem is the optimization problem, which is I want to tune my model to a certain environment. Maybe I'm going into an environment that hasn't been measured before, and we need to come up with some estimates for what typical losses do exterior walls and trees and shrubbery and interior walls and other types of partitions. What do they actually do to this new frequency or new configuration of transmitter? Maybe if the transmitter's brought down low to the ground, that will often change the interaction in the environment and will tweak these numbers. Or you could just change the frequency of operation. That's another way to make a change in the environment. And for the optimization problem, you take a bunch of measurements of path loss or received signal strength, and you're trying to get the model parameters out of that. Now, take a look at this. One of the nice things about the partition-based model is you can organize everything into a matrix. And that's important as a first step if we want to try to reformulate to solve an optimization problem. Computers are, of course, very good at doing matrices. Matrices, there's nothing particularly special about them. They're just a bookkeeping scheme to organize a lot of data. So if I have a bunch of path loss data, and what I have here are dB path loss with respect to 1 meter free space in this column. And I take a bunch of measurements, or I want to try to get a bunch of predictions. This is path loss at location 1, path loss at location 2, all the way down to the nth path loss. Each of those, of course, has a TR separation distance measured in meters. Distance 1, distance 2, all the way down to distance n. And the way that we formulate the partition model values, we have a matrix A, which has all of the site-specific information in here. This is our site-specific info. So for location receiver 1, I have a number, probably an integer, that represents the number of, say, walls, exterior walls, interior walls, trees, forests, whatever you want to try to correlate your information with up here. And then for the second point, you have those exact same parameters, just changed to accommodate the intersection test that you're doing, all the way down to the nth point. And this is a nice way to write the Seidel-Rappaport formula because it makes the prediction problem seem just like a simple matrix equation. P, path loss, is equal to 10 log base 10. This paper is using distance. And keep in mind this is a distance vector that has all the points. And this log here is operating not unlike MATLAB code, element by element on D. It's not doing a fancy transcendental matrix operation. It's just operating on the elements of D. And then I can write simply all those extra loss contributions as A times the vector X. X are my dB per partition values. And this is the modeling problem. Give myself a little more space. I have a bunch of unknown locations I want to model. I just need to calculate their distances, the geometrical information, and look the partition losses up in a paper, and I can calculate it very easily. If I fill in all the information on this side, then I have a nice system that has n unknowns over on the left-hand side and n knowns on the right-hand side, so it's a very straightforward calculation. For the optimization problem, what we're trying to solve for is x. So we can rewrite this equation as ax equals 20 log base 10 d. And that should have a minus sign. We're going to move that over there. And we're subtracting that from our path loss values. So we take the path loss, we subtract off the free space loss, and whatever residual error is over here, we model it with this equation. Now this is a problem here because usually I only have several, 2, 3, 4, 5 partition values that I'm trying to solve for here. And I have a lot of, hopefully, I have a lot more data over here. So I should have a vector that's basically n by 1, where n is the number of measured points. And that is a over-constrained problem. Because if x only has 3 or 4 unknowns, and I've got a whole mess of data over here to calculate it, then I have to figure out a way to find the best solution. But we do want an over-constrained problem because there's a lot of variability and a lot of error in this and any other modeling technique for radio propagation prediction. And so we need to find a way to pick out the best solution, the one that results in the minimum mean squared error. And so you may have seen this in the context of other problems, but there's a straightforward way when things are in a linear matrix form like this to solve for the minimum mean squared error solution. First, you take both sides and you multiply by A transpose. This is nice because at this point A should be like a 3 or 4 column across and an n matrix, so it should be a highly rectangular matrix. We take A transpose and multiply it, we'll get basically, if this X has m elements, we'll get an m by m resultant from that, a square matrix, which of course is then invertible, and then I can solve it. And it turns out that that's exactly what this equation is. This equation actually has a special name. It's called the normal equation. And solving the normal equation gives you the minimum mean squared error. It's a global solution too. You can show that this is the best you can possibly do for this simple linearized model. So all you have to do is get down here and say ATA. You got to invert that and multiply it by both sides such that x is equal to ATA minus 1 times AT times my data vector with the free space. Subtract it out. And there it is. That's the solution. So if you have a bunch of data points here, then you can plug them in, calculate your data, and then do A transpose A inverted times A transpose, and you'll get the best possible solution, the one that minimizes the mean squared error between prediction and measurement, at least prediction and these measurements, that whatever you've taken for this particular environment. Remember, there's always interesting ways to build in biases and other sorts of errors in your experiment. So you do have to be a little bit careful. But really what we're doing here is a standard operation in data science, really, which is finding trends, capturing the correlations between observations and, in this case, environmental information. This approach is generic. This is math, so it can work on anything. So if you wanted to make a system in which, let's say, you were going to do B is the stock market price on any given day. So $1, $2, $3. And let's say you have a whole bunch of historical data on that. And you wanted to suspect that, or you did suspect that, that price was correlated with maybe, we'll call this first element the price from 1 week earlier. You could do the cost of oil on the day that you were predicting. And you could try something really random, like, days since the last Falcons win. Maybe the universe has some peculiar correlation with how the Falcons perform. I don't know. The point is, you can pull it out with data like this. So you populate all this data into an A matrix for every measured point you have, and then you have a system, AX is equal to B. This is your hypothesis. And you solve this with the normal equations. And out will pop hopefully meaningful values. If it turns out there's probably a big correlation between the value of the stock market and its value from 1 week ago. So this probably would be a high correlation over here. 0.9 or something like that might be the value. It turns out that there's probably a weak dependence on the cost of oil. And so there'll probably be a small number here. It will probably be negative, because generally, as a rule of thumb, if oil goes down, the stock market usually goes up in the short term. However, you might be able to spot some weird correlations over time if you do a more advanced analysis with more vectors with different oil values in them. And then finally, days since the Falcons' last win. Our intuition would tell us that there should be very little correlation between the stock market price and whether or not the Falcons wins, unless an enormous number of investors are themselves Falcons fans and are demoralized and get very pessimistic and bearish about finance whenever the Falcons lose. But my guess is that this should be close to zero. And so there you go. Now you can do some financial modeling and join a hedge fund as a consultant based on your knowledge accrued in antenna engineering. Let's do a sample problem here, just to make sure that we understand what's going on. Okay, here's a problem that comes right off of the test. Propagation modeling. Below is a sketch of a building floor plan with a 2.5 gigahertz wireless local area network and an access point. The access point transmits 500 milliwatts into an antenna having 2 dBi of gain. Included on the sketch are several signal strength measurements taken from a handheld Wi-Fi terminal with 0 dBi average receiver antenna gain. You are asked to construct an optimized Seidel-Rappaport propagation model that includes soft partitions for cubicles. You see by the key, that's what these black lines are. Hard partitions for plaster walls. That's these thicker gray lines through here. See that over there? Write the A matrix and B vector you would use to solve for the optimal model. Populate these quantities with numbers, but do not solve the system. Only rough estimates of distance are necessary. No need for a ruler. Look, I have this very sophisticated ruler attached to the diagram of the building. Now, there's a lot going on in the description of this problem, but it's very easy, and in fact, you don't even need to solve the system. That's actually very important because not only is it cumbersome to have to compute inversion matrices on tests, which does not really test anything related to concepts in antenna engineering. But this square matrix formed by ATA is actually a very difficult matrix to invert. Most modern solvers don't have much of a problem with realistic data. But ATA is always an intrinsically ill-conditioned matrix. In the olden days, i.e. the days I went to school, we had to be very wary of that because matrices often, when they were ill-conditioned, they were difficult to invert, and you had to bump up your precision or do something else to make sure that you could flip the thing. Not as much of a problem anymore with modern computing. Okay, now, we know, let's just write the logarithmic link budget equation, and we'll plug in all of our stuff. 20 log base 10, and that's 4 pi over lambda, and then minus path loss. Okay, so there is our equation. What do we know? Let's plug stuff in. First of all, this is 0.12 meters. How do I know that? It's 2.45 gigahertz. 2.45 times 10 to the 9th divided into the speed of light, which is 3 times 10 to the 8th meters per second. This is per second, or hertz. Gives me my wavelength. And I just happen to know it's 0.12 meters because I've done that calculation for 2.45 gigahertz 100 times. Thousands of times, probably. It's 12 centimeters. Now, the problem said that the receiver that you use to walk around this building that Professor Durgan invented with his imagination, I'm not an architect, as you can see. As you walk around this building, you're taking it with measurements with a 0 dBi antenna. So that's a 0 dBi. This transmitter has a 2 dBi antenna gain. Not much, so it's not very directional, probably broadcasting. And what is the transmit power? 50 milliwatts, also known as negative 3 dBWs. If you take 10 log base 10, the value of watts. So that's minus 3 dBWs, or 27 dBms. If we convert that to decibel milliwatts. You just have to add 30 if you're going from dBWs to dBms. Now, when we see a received signal strength of, say, neg 65 dBms, to calculate the path loss here, all we have to do is basically move that over to this side of the equation and this over to that side of the equation. So we just have to plug in, and so B, T, And we'll have use a little subscript since we have multiple points we're going to be doing this to. At the ith location, the path loss is going to be equal to the transmit power minus the ith received power plus g sub t plus g sub r minus the path loss at 1 meter free space, which we can plug in our 0.12, and that should be it. Well, yeah, that's good. That's good. Now, if we wanted to, we could furthermore define B to be equal to path loss minus 20 log base 10 the distance. And we can go in and calculate the distance for each one. This one looks to be about 3 of these units, so that's about 15 meters. This is probably close to 15 meters. There's about 2 of those units. I'm going to call that 10 meters. And this is probably also 15 meters. So basically, my D vector is going to be, if I call this 1, 2, 3, 4, it'll be 15, 10, 15, 15 meters. And then my A matrix, I've got to construct that. That was really not that hard. All I have to do is count the hard and soft partitions. So I'm going to make this the hard ones, the thick gray ones, and then the soft ones, this column. Location 1, if I draw a line, it goes through that doorway, I'm going to say it only goes through a hard partition once. For number 2, it goes through a hard and a soft, it looks like. I'm going to put 1, 1. Over here it goes through a doorway again, a hard partition and a soft partition. 1, 1. And this one goes through a hard, and no soft partitions. So I'm going to call that 2, 0. And there, I've defined everything. So I know that AX is equal to PL, the answer's up here, minus 20 log base 10 D. And you know what? I'm just about done. If I wanted to, I could write the normal equations. And so there it is. I could leave this problem like this and I would get full credit because I've defined all my matrices. Maybe I'd want to write out the numbers in my path loss matrix. And I say, put these in this formula and that'll give you the right answer. No need to solve. I'm not here to test your ability on plugging things into calculators. Not at this level. So there's an example of a fairly quick problem to do on a test. Okay, well, after this lecture, we leave the world of large-scale path loss and we start to talk about small-scale fading, which is this sort of irritating phenomenon that you can never really get rid of in a realistic link. But you just have to cope with it. And that'll be the next topic.